Okay, guys, so we're going to do these pretty quickly. And I guess if you have questions, I hope that you can let me know about that. When we have an acid in the presence of, when we have an acid in the presence of an alcohol, what we get is a dehydration reaction occurring there, and you end up with a double bond. On the opposite side, if you end up hydrating that double bond, you will end up having to pick which direction the OH goes. And due to Markovnikov's rule, that's going to go over there on the one that's more substituted. This reaction we haven't covered, so I'm going to cross that out. Next, we have water and H+. So as we just did, we are going to make a double bond. It doesn't matter if you draw it in this direction or if you draw it in this direction. The point is that the double bond does not go on that methyl group that's right there. So if you have something with H2 and Pd that gives you an alkane, it doesn't matter where you put a double bond as a reactant, just that you have a double or even a triple bond somewhere. So, I mean, it really doesn't matter where you put that. All of those answers would be correct. Okay, 2 more left on this page. In order to get an OH on the most substituted carbon, we would need to add H3O plus, or you could say an acid and water, whatever that may be. And that would be it. The next here is just a reduction reaction. So reduction would be all that you needed to write in, at least for now. On the next page, this is asking you to determine if the following alcohols are primary, secondary, or tertiary. We talked about that like a teeny tiny bit, so I'll do it for you, but don't worry about this too much. This alcohol is attached to one, like this carbon, and so we would define that as primary because that carbon's only attached to one more carbon. This carbon's attached to 2 more carbons, so I would say that's a secondary. The carbon that this one's attached to is attached to 3 carbons, so that would be a tertiary. This carbon's attached to 2 more carbons, so that would be a secondary. Skip this, we didn't even talk about polymers. This is much more important. We need to rank the boiling points in each of these examples. Well, here we have alkanes. Here we have a ketone that has dipole-dipole interactions. And here we have an alcohol that has hydrogen bonding. So hydrogen bonding is going to rule. It's going to have the highest boiling point. The dipole-dipole will be in the middle, and the alkane will be lowest. Now, we've done other examples. We haven't talked about this too much, and we're going to later, but not right now, but that's okay. I want you to look at these molecules and just realize that the longer you have a carbon chain, the less like a functional group will matter as to what it is. So in other words, we have this carbon chain on this guy versus this guy. Well, on the first example, we have 4 carbons that are there for 1 OH. For this guy, we have 2 carbons that are there for 1 OH. What that means is the effects of this OH are kind of diluted on this in comparison to this one. So if you have a longer carbon chain, the hydrogen bonding is not going to be as effective in sticking molecules together. Now this one over here has 2 of them. I don't want you to worry about this right now. We'll come back to that later though. Okay, let's do some more reactions because that's probably more relevant. When we oxidize an alcohol, we're going to end up with a carbonyl, C-double-O bond. And when we reduce this guy, we're going to end up with an alcohol. Skip this, I won't give that to you right now. To get from an aldehyde to a carboxylic acid, you would oxidize. And in order to make an alcohol, or at least a primary alcohol, you need an aldehyde. And that's it. I hope that you got those all, and I'm sorry if you got confused with the other ones, but as I said, I made this long ago, so I hope that this is helpful. Thanks.